And with that, I will hand things over to Jeff. Thank you.
Thanks. I'd like to remind everyone that the Rensselaer Plateau sits within the ancestral and traditional homeland and territory of the Stockbridge-Munsee band of the Mohicans, who stewarded this land before they were forced to move west to Wisconsin by European settlers. Some Mohican people remained in New York, and some have returned home from Wisconsin. RPA cares for this land today with deep respect and gratitude for the Mohican Neok. These are the people of the waters that are never still. And we still build lasting partnerships with and to amplify the needs and perspectives of local indigenous communities. Tonight's speaker, Dr. Dave DeSimone, affectionately known as Iceman to some of his students, has lived on the Rensselaer Plateau since 1994 and has spent most of his career as a professional geologist, balancing the multiple responsibilities of teaching, research, and consulting work. He's taught at Williams College, RPI, St. Rose, SUNY New Paltz, Bennington College, and he was able to participate in glacial geomorphology research in far-flung places, including Alaska, Yellowstone, San Juan Mountains of Colorado, and of course, Rensselaer Plateau. Dave's consulting work is primarily as a geoarchaeologist working with local cultural resource management and engineering firms. He usually studies soil and sediments exposed in backhoe trenches with archaeologists. Dave is actively engaged in Pleistocene geology research, primarily in New York and Vermont. He has mapped the superficial geology and aquifers in New York and Vermont as part of the USGS State Map program. In 2015, Dave was a geoscientist in the parks. That's a geologist at Saratoga National Historic Park, a National Park Service joint program with the Geological Society of America. There he generated superficial and bedrock maps of the National Historical Park area. Dave recently completed mapping superficial geology for the Hoosick Falls and Petersburg to better understand PFOA contamination in a project funded by the Hoosick Falls Consolidated School District. Concurrently, he mapped PFOA contamination in the region in Bennington, Vermont for the Vermont Agency of Natural Resources and the Vermont Geological Survey. He's been given public talks on history and geology to the Rensselaer Plateau, where he's lived since 1994. So I'd like to turn it over to Dave now, or Iceman, as he's sometimes known.
So can everyone hear me now? Is it working out all right for you? You have a little background noise there. I do have a nearly 4-year-old who's running around the place on a bit of a sugar high and just came up the stairs with my sister who's babysitting. So I'll just have her say hello real quick and then take her downstairs. Say hi to Arya to everybody.
Hi, Arya. Hi.
Hi, everybody.
Hi, everybody.
Yeah. You want to go down with Kathy while I talk? Go with Kathy, okay? I'll be up here. I'll see you soon. So Jeff's intro was very kind. Someday I'd probably like to tell you the story of the geoscientists in the parks. There's a very long history to that having come about. And I wound up having to do a lot more than I bargained for because I thought I'd be doing a superficial geology map of just the park, and I ended up doing a superficial geology map of all 4 quadrangles that encompass the park. And then they said, well, you probably ought to do a bedrock map of the 4 quadrangles as well. And guess what? We don't have much money to give you. but it worked out fine, and it was a pleasure to do. Working in the park took me all the way back to my master's thesis mapping of the Schuylerville quadrangle, and we'll take it from there. A little plug for my archaeology friends. Sorry here, there's a little bit of background noise that's coming in.
No, I'm not happy. Get in your room.
Hang on a moment. Sorry, but you can hear there's a little stuff going on over here. Can I pause you guys for a brief moment?
I think you're okay. They're not very disturbing.
I'll just do a stop screen share here for a minute. Hang on. Sorry about that, but hang on a minute. I'll come down and take care of you for a minute. Hang on, folks. You have to go with Kathy in the other room.
Zoom.
Jeff Briggs, how's everything out of Poston Kill Community Forest these days?
Just dandy.
I'm glad to hear that.
Little snow, but it's gone now. So the trails are wide open for hiking. Everybody's welcome.
All right, sorry about that brief delay. Let's pick up. I wanted to make a connection with Bill Kelly's talk several years ago about the bedrock geology of the Rensselaer Plateau. And I thought the way to do that was to just provide a little bit of a summary, but to make that a little bit more favorable in thinking about why is the plateau high terrain now surrounded by the lowlands of the Little Hoosic and the Hudson lowland? Why does it stand proud in high relief?
David, I'm sorry
Yes.
to interrupt, but you're not sharing your presentation anymore, so we can't see
Oh,
your slides
sorry.
right now.
Sorry.
No problem.
There we go. There we go. A little bit of a side track there with my daughter having a little meltdown. This actually, if you, those of you recall Bill's talk, this was
All right,
one of
David,
his
just
slides as well.
one
Pardon?
Sorry, David, one more thing. You're still in presentation view, so if you could just full screen it, and we should be all set.
I'm going to leave it this way for now.
Okay.
I'm not able to see my cursor when I go full screen. And Bill was telling us about the origin of the Rensselaer Graywacke from a tectonic structural geology standpoint, since that's Bill's specialty. I'm going to come at it with you using the same slide here, that Taconic was a Japan-style of volcanic arc off the coast of eastern, what would be now eastern North America, the Laurentian shelf. And subduction was happening under that volcanic arc as depicted in the top cartoon. Where's the Rensselaer Graywacke come in? As that volcanic arc is being eroded fairly rapidly rising, rapidly eroding, the sediment from that arc is being deposited into this closing ocean, and a very unstable shallow water, deep water transition allowed for sediment deposited originally in shallow water, sand and mud, to cascade down submarine canyons that were along the edge of this island arc, volcanic arc, or must have been, to deposit that sand and mud in a deep water environment. As in the geosciences, we think of sandstone, any variety of sandstone, as being a shallow water deposit, a beach, a dune, a nearshore deposit. But in the case of Graywacke, a poorly sorted sandstone, there's a lot of mud in it. It has some unique characteristics that tell us about its origin. And it was deposited in deep water at the foot of a submarine canyon as a large submarine fan. Once this oceanic slab is consumed and the volcanic arc is accreted onto the edge of eastern North America, Laurentia, all of that sediment is contorted and shoved up in a taconic style, shallow thrust fault setting from east to west, as you see in the bottom cartoon. And the Rensselaer Graywacke is one of those thrust faulted slabs of rock, but it stands tall now. Here, some of the features, there is a hand that you can see over here. I think it's probably my wife, gloved hand in a black glove. You're looking at some bed forms at the base of a Graywacke layer within the Graywacke. Those bed forms were formed by erosional scour as one of these scubalanches, a term that I think I coined years ago at Williams, scoured the slope down which the sediment cascaded in a submarine avalanche, hence scubalanche, and deposited that sediment onto the floor of the canyon. Once the velocity slowed, those scour marks were filled in with the sand. And that sand can also contain some clasts that were originally deposited in shallow water offshore. The dark clast that you see here is a clast of what was mud in a shallow water marine environment and came down slope with the scubalanche and was deposited, here the Leatherman for scale, along with some other sand, pebbles, and eventually mud in a layer of sediment that represents deposition from one single event, that single event being a single scubalanche. In between these scubalanches, what officially in geology we refer to as turbidity currents, turbidity flows. So a Graywacke is a turbidity current deposit. In between, you just have mud settling on the floor of the deep ocean basin. That's off the west side of this Japan-style volcanic arc. So a single event alternates with perhaps hundreds of years of mud being deposited, then a scubalanche, mud, then a scubalanche, more scubalanche, more scubalanche. And you build up a fan of sediment, which in the case of the Rensselaer Graywacke is predominantly graywacke, not so much shale. If we go off to the fringes of the plateau, as this picture was taken, you see a lot more shale, but very little graywacke. There's still one turbidity current deposit, another small one, but mostly you're seeing shale, which is the Nassau Formation around here. So that's our summary of Rensselaer Graywacke. Where is it? Where does it come from? It forms from turbidity currents, aka scubalanches, that carry sand and mud down a very steep slope into a deep water environment, deposit it as a subaqueous fan at the mouth of a submarine canyon. The Nassau Formation is a weaker rock. It's much more easily eroded. It's the rock which underlies west of the plateau, underlies the area along Route 7, Route 2 as you come toward the outskirts of Brunswick and Troy. The Graywacke is robust. It now stands topographically high from the surrounding shales because it's much more resistant to erosion. It's not the most resistant rock to erosion, however. If we go farther east from the Rensselaer Plateau, you go up to the Petersburg Pass on Route 2, you're into the tectonic phyllite, which is more robust than the Graywacke and stands higher than it. And if we go farther east to the Graywacke, to the Mount Greylock schist, that is more robust still, and hence Greylock stands up as the most resistant rock in the immediate neighborhood of us. Let's switch gears, looking at relief. Physiographic regions of New York. This is a DEM I pulled off the internet. It shows you the upland regions, the Adirondack Mountains, the most resistant rock in the state, the Catskill Mountains, an ancient Devonian age delta, Silurian and Devonian age. It also shows us 3 plateau regions in New York State: the massive Allegheny Plateau, dissected by the Finger Lakes, the much smaller Tug Hill Plateau, and here we are, right? The Rensselaer Plateau is a small physiographic region of New York, but one that, you know, some of us call home and some of us enjoy working in and playing in as well. We can see the rest of the tectonic geology is here. The Rensselaer Plateau is one of numerous subaqueous fans that carry down to other sections of the tectonic orogeny that happened in the early to mid Ordovician. Our lowlands in this DEM, the St. Lawrence, Ontario, Erie lowland, the Mohawk lowland, the Ontario lowland and Mohawk lowland converging, if you will, in the middle of central New York, Utica vicinity, and this major thoroughfare for ice, which is the Hudson Champlain lowland, which is a very prominent north-south ice streaming lowland, if you will. Ice could flow without obstruction down this way to make it out onto the dry continental shelf during the Pleistocene. So the lowlands formed where the rock was weakest. Streams eroded the rock. Glaciers have deepened and scoured smooth those lowland regions. The St. Lawrence, Erie, Ontario, Hudson, Champlain, and Mohawk. The highlands, the resistant rock is at the land surface, Adirondacks, Catskills, Taconics, in that order in terms of susceptibility to further erosion, if you will. Switch gears, take us to the Pleistocene. We're thinking about Pleistocene history of New York, global glaciations first, New York glaciations, and then what we're learning as the initial phases of work with the Rensselaer Plateau. it's something I've always tried to impress upon students, but when you look at a map of North America and you take the size of the Antarctic ice sheet, the combination of the East Antarctic and the West Antarctic ice sheets, and you put that down on a map of North America, you've pretty much matched the size of the Laurentide ice sheet plus the Cordilleran ice sheet. And it's impressive. It's impressive when you think about how thick that ice was. Here are contours in meters of the Antarctic ice sheet, comparable to the thickness of the Laurentide ice sheet. You're looking at 3,500 meters, roughly 10,000 feet, 2 miles of ice at its thickest. Here on the Antarctic ice sheet, the East Antarctic ice sheet, through the elongate dome, dome A, even reaching 4,000 meters in thickness. How do we know about the Ice Age climate change? Now we have hard data that comes from the analysis of ice cores, sediment cores from the marine environment, ice cores from Antarctica, from Greenland, from little bits of alpine glaciers that still survive in South America and in the Alps, for example. One of the best cores was drilled here at Dome C. The Epica core penetrated some 3,300 meters of ice some years back. This is not exactly the newest information, but is the deepest ice core that we have. And the longest history going back some 800,000 years. This is the Epica ice core that's being extracted from the auger bit by a technician, obviously kept in a cold room. Much of this ice core is stored in a facility in the Rocky Mountains in Colorado, for example. And if we look at what that data from the Epica ice core reveals, and you can tell this is a few years old, this slide, with parts per billion methane, we're now over 1,800. And with parts per million CO2, we're up over 400 now. I don't really know what the latest number is, whether it's 405, 404. Maybe someone will chime in later with that. But this cartoon of the data depicts temperature anomaly, and carbon dioxide and methane are two worrisome greenhouse gases that we think about. And it's very obvious that there is a strong positive correlation between temperature change and the amount of CO2 and the amount of methane in the atmosphere. If we zoom in and look at just the last 400,000 years of ice, again revealed from the Epica ice core, as well as some other ice cores, the Vostok ice core going back many more years than that, penetrated back 400,000 years as well. What we can say with certainty and in a broad brush way is that cold climates were dry and dusty. This is your dust peak at the last glacial maximum in terms of temperature, and in terms of CO2, the last glacial maximum being under 200 parts per million CO2, about 170, 180, to the peak of an interglacial where routinely CO2 was up around 300, 320 at the most during a normal interglacial, as opposed to a heightened interglacial that we're in now. But cold times, dusty climates. What you often don't think about is that much seawater locked up in fresh water ice on the land took sea level down quite a bit. And here at the last glacial maximum, marine ice stage 2, if you see MIS2, marine ice stage 2, isotope stage 2, you have a range here of some 120 meters to as much as 140 meters, depending upon the data sources, for how much sea level was lower. If you go midpoint, 130 plus or minus 10 meters lower than today, that's what, nearly 400 feet lower. So much of the continental shelf of Eastern North America was exposed. If we look at this now in a real cartoon fashion, but there's our Antarctic ice sheet plopped down over North America. That's about the same size, same thickness, same volume of ice that Antarctica represents now that covered North America during the last glacial maximum. A little bit about local evidence that big ice, and we think of ice sheets as representing big ice, was here. And these harkens back to classical evidence for ice ages. 3 types of classical evidence as first recognized and studied in the Alps are striations, erratics, and moraines. I'll go off to the side on a short tangent and let you know if some of you are interested in reading and learning about the history of ice age science. How did the ice age theory come about? How did it come to be accepted, which took about half a century for it to become accepted? There's a superb book which has a bit of a local flavor in it. And it's called The Ice Finders by Edmund Blair Bowles, B-O-L-L-E-S. It's a book I would assign in classes that I taught about glacial geology and climate change. The subtitle of the book, How a Poet, a Professor, and a Politician Discovered the Ice Age. I highly recommend it. It's a really good book to read. But striations, erratics, and moraines first recognized in the Alps. Classical evidence for glaciers locally. Striations, Bennington, Vermont. This was seen during mapping for the PFOA study in Bennington and North Bennington. This is actually near the North Bennington primary contamination site, but you're seeing carbonate rock, which is a fairly soft rock, which is taken, if you will, preserved the parallel scratches that you see. And this is kind of cool because it's on a vertical surface. They are also present over the top of this as a horizontal surface. It represents the ice that was flowing and surrounding this bench, this knob of exposed rock, which is actually behind one of the warehouses there in North Bennington. Here locally in Grafton, my key showing you the approximate direction of the prevailing direction of striations here in Grafton, right off Route 2. This is near Gundrum's lumber yard, right near home. Classical evidence for glaciers, erratics. And you can tell that this is Grafton Lake State Park. The parking lot is in the bright tone in the background. This is one of the boulders that's undoubtedly been, or maybe not, been moved around a little bit. I doubt it's been moved far. If it's been moved at all to clear for the parking lot. Classical evidence for glaciers, a moraine in Woodstock, New York. This was a photo taken with one of the students working on an REU undergraduate research project run out of New Paltz that I did with John Rayburn, friend and colleague. When glaciers erode the landscape, what do they generate at their base when they erode? They transport boulders the size of Volkswagens or larger. Sand, silt, clay. The primary volume of sediment generated by a glacier is silt-sized particles. All of this can be deposited directly by the ice and represents a type of sediment we call till. All of this can be picked up by meltwater and deposited as sand and gravel on the land as an outwash plain or into shallow water, maybe forming a delta. And the finer grain stuff, the mud, the silt plus the clay, usually won't come to rest in a standing body of water unless that body of water is pretty deep, as parts of Glacial Lake Albany were. Just a couple of examples of that here. Glacial deposition under the ice. Here's an exposure of till in a tree throw in Hoosick Falls. This exposure was near the railroad tracks, just off the entrance road to the sewage treatment facility at the northern end of the village of Hoosick Falls. What you see here is everything. Cobbles, silt, clay, pebbles in a largely unoxidized gray sediment because it's getting deep enough in this tree throw to get you into unoxidized versus the oxidized tan sediment. But it's an admixture of all particle sizes transported by the glacier and deposited directly under that glacier. Here's something where sediment is much more sorted, much more dumped, if you will, in this case, dumped into a body of water by a stream. In this case, not a meltwater stream, but a meteoric stream entering Glacial Lake, Quaker Springs in the Champlain Valley. It's the Street Road Delta on the New York side of the Champlain Valley. It's the northernmost deposit into the lake that had the level of Lake Quaker Springs. We go a little bit more locally than the Champlain Valley. If any of you folks wander up Route 40, Spiegeltown, Warren Faines, big operation. This is an older photograph taken from one side, looking back at the big power line with the sand dunes on top of it, or under the power line, but the sand dunes at the top of the pit. This pit shows you layers of sand that are rippled, that fine and get finer grained, finer grained, finer grained until you finally come up with clay. And this clay was probably a shallower water backflow area, something that was somewhat inhibited from currents and was quiet water because it's a localized lens of clay here in the deposit. But just to give you examples, wind can also blow the sediment around. The pine bush, where my daughter and I love to hike, is a place where windblown sand of a very well-sorted nature accumulates. This is off Washington Avenue in one of those geoarchaeology projects. Here, back to Hoosick Falls, sediment deposited in deep water in a glacial lake typically forms varves. What's a varve? A varve is a couplet of sediment that represents a seasonal deposition. Mud, which is some clay and some silt, deposited in the winter. And the summer, you get the oxidized tan color of silt and some fine sand. Back to winter, unoxidized gray. Back to summer, winter, summer, winter, summer, winter, summer. I think I've probably counted about 14 varves in this exposure, which is near the bus garage for Hoosick Falls, right off of 22. How do we use these varves? We've already addressed what they are. This gets us a little bit of fun. This is some fun that a couple of my friends and colleagues call fun. I don't know if you guys would call this fun, but there's me kind of unluckily standing under the ladder. I don't know why, but it was the best place to get a grip on the core that we're retrieving from the southern end of Lake Champlain. Late one winter day where John Rayburn, who's I'm facing, is also pulling up the core. It's his coring device. And you can see from the knees down on top of the ladder is Dave Franzi from Plattsburgh. And who's taking the picture is no one other than Bill Kelly. I don't know why we dragged Bill out into the field to help us drill this. It must have been the promise of scotch or something. I don't know if Bill's watching or listening. He'll get a kick out of that. I decided I would, since I was wearing the oldest pants, those pants date from 1953. They're older than me, although not by much. Korean War surplus from the Australian Army. I decided, well, I should take a rest and take over the camera, but there's Bill, John Rayburn, and Dave Franzi, who's, you can see from the knees up at least, working to extract this core from Champlain, shallow end of the Champlain basin. And what does this look like? If you pull apart one of these cores, you can really count the bars, but better than that, you can match them up from one place to another, to another, to another, to another. And you have hundreds of cores retrieved from hundreds of places. And assuming you get the overlap, the pattern of thick and thin barbs is easily matched. In this core, which is not the one that was retrieved in the previous photos, you take it all the way down to Till when the ice was there. When the ice left in the Champlain, you had a glacial lake, which froze over in the winter, and you have a thin winter layer and a thicker, warmer summer layer. A few models to take us forward to understand how we do glacial geology. Ice terminating on land can deposit any of a suite of landforms that reflect deposition of till or sand and gravel or silt and clay deposited maybe in a small puddle. Ice depositing into deeper water. And for this, the reasonable example is to think about Albany, Troy, Saratoga, the Hudson Champlain lobe terminating in deep water of Glacial Lake Albany. You have a suite of landforms. There may be the moraine that's deposited under the ice where the ice begins to float. You may have sediment built out into the lake, which could build up and become a delta. You may have sediment dropped from icebergs, which can be easily recognized as an iceberg deposit as it plops into the bottom after a big stone or a big chunk plops into the bottom. And you decipher the landforms to tell you a story about history. The next step is, once you generate a map of glacial landforms and sediment, remember this is a sediment map, so it's also a soils map. You then have to decipher the history by taking it in a time sequence. This were cartoons I generated way back from my dissertation defense back in the mid-80s, 1985 to be exact. But in places like where we are in the Tectonics, where there are little valleys, there's a little tongue of ice that may have been extant in that valley, and then another one in the next valley, and another one in the next valley. And each one of these little tongues of ice has its own suite of sediment with accordingly demonstrative landform that will tell you the story of what happened as the ice retreats up this valley and up this valley as the margin retreats. Again, T2, we've taken and changed the environment, the depositional environment at the margin of the glacier. The lake may be a small puddle, a proglacial lake, which the ice has retreated out of. And in this little valley, the ice retreated from a moraine and formed a lake as it retreated. And now it's maybe floating margin into the lake. And in another setting, the ice may have stagnated and melted and left behind a thinned, wasting away piece of itself, and then retreated back. So this is how we do the business of understanding the history of the ice retreat globally, regionally, locally. Let's deal with New York here as we come close to an end. Yeah, these critters did roam Grafton. I used to like to throw in a slide like this when I'm talking about the local history. Once the ice retreated, we can define ice margins that give us at least this approximate view of the shrinking Laurentide ice sheet over time. And recognize that as the ice sheet was shrinking, getting areally smaller and substantially thinner. That meltwater is refilling the sea, and in a non-linear way, sea level increased since the end of the last glacial maximum. Moraines is a cartoon from a textbook, which show you the two moraines that comprise Long Island at the terminal moraine and the first retreating moraine at the northern shore of Long Island. But note the terminal moraine blocked the Hudson Valley and enabled the existence of a glacial lake in the Hudson Valley as the ice retreated northward. That takes us to a different canned cartoon from a textbook, which shows you how easy it is. I envy people who do their work out in the Midwest where you can walk on these ice margins. The moraines just go for tens, even hundreds of miles, and you can just walk on them and drive over them. You get to beyond central New York and you get into eastern New York and throughout New England, we don't have these beautiful moraines because we have high relief terrain. That takes away the opportunity to have well-developed, continuous looping moraines. So how do we decipher the history here? The figures that we're wrapping up the talk with are coming from, this is the physiographic regions, but these come out of Franzi et al. Dave Franzi, myself, Jack Ridge, John Rayburn, a couple of others, Dave Barkley. We put together a fairly recent summary of our understanding of the glacial history of New York. And these figures are from that. This one is one that we inserted. This is Jack Ridge's data from Tufts University, where this is publicly accessible information. Jack is the guru of VARVs. He's assembled all of the VARV data throughout North America. It used to be called the New England VARV chronology record, is now called the North American VARV chronology record. And from that record, we can depict the retreat of the ice from the Hudson and Champlain lowland with dates on the ice margins. We take it back a little bit here when the ice is still south of the Hudson Mohawk confluence, but we've opened up the Mohawk Valley to Glacial Lake Schoharie. Lake Albany has expanded northward. Let's take a look at the Rensselaer Plateau using the RPA website map, LiDAR imagery. The first step we now do in understanding glacial history is to look at LiDAR. We used to look at stereoscopic air photo pairs, technology that goes back to World War II and before, to see terrain the way you can see it in a LiDAR hillshade map. So this is my first step in trying to understand the glacial history of the Rensselaer Plateau. And I'm in stage one. I'm looking at LiDAR, and I've just barely begun to understand whether what LiDAR indicates as being present is really present, or if it's a figment of my imagination in viewing the LiDAR. And if it is a figment of my imagination, let me take a quick look at it. In yellow, you see LiDAR hashtag, if you will, quote unquote, indicated ice margins. I've looked at the LiDAR and seen the potential for something that represents an ice margin. It might be a tiny fragment of moraine. It might be a place where there's a meltwater channel that heads or begins at one of those little yellow squiggles. There might be a deposit that's perpendicular to an ice margin, which might or might not be an esker. And I've drawn those in with the recognition that in order for them to be real ice margins, I have to verify them in the field. So there's a lot of footwork to do, whether I'm doing it or someone who succeeds me comes along and does it. There's one ice margin on this map that's not in yellow, and it's in blue, and it's something I've just nicknamed the Babcock Lake ice margin. It's there, it's here. I'm sitting on it. It's where we live. There's an old cane terrace represented by the ice coming out of the lake and wrapping around into Fox Hollow. There's an esker or crevasse fill across the road from me that was exposed in the construction of a home that we have a new neighbor of. Where I live was a former gravel bank. And when we were excavating for the foundations for the house, I could see with shock, but with the understanding that that's why I bought the land. It's gonna perk, Dave, because it's sand and gravel. It's not the usual crappy till that you get in the Rensselaer Graywacke terrain. So there's a verified ice margin here, and it's the only one so far. Third thing we can do is, as I indicated, use the LiDAR suggested, LiDAR indicated ice margins to show me where meltwater may have escaped from the margin of the glacier and gone somewhere. This ice margin at the very top of the image represents the Hudson Champlain lobe blocking the Potter Hill outlet at 900-foot level of Glacial Lake Bascom in the Hoosic Valley. That must have produced quite a torrent of meltwater that came down, heading off the lower flanks of the plateau and out into the Hudson lowland and getting us into central and western Rensselaer County. But that outlet at Potter Hill, recognized by Frank Bursley Taylor back in the early decades of the 20th century, he first looked at this. Getting us back to the regional picture, Lake Albany, as the ice retreats, starts dropping through lower and lower levels that may not have persisted for any significant period of time. One of them called Lake Quaker Springs. One of them called Lake Colville, which existed as far south as the outskirts of Waterford, where the Half Moon Moraine served to block it. Lake Colville, although it wasn't the threshold for the lake may have been somewhere else. We're still looking for it. But as the ice retreats, the lake, Big Lake, Lake Iroquois in the Ontario lowland, and Lake Colville in the Champlain lowland, hard to say it's in the Hudson. The ice retreating some more, and at some point before the ice retreats enough, where Covey Hill here is exposed, you have the last vestige of high flow down the Mohawk River, which forms the Cohoes Falls that we see in probably a very short period of time. Once the ice retreats from here, the Mohawk River, the Iro Mohawk, is shut off, and all of that outflow from Glacial Lake Iroquois goes into the successor to Lake Colville, and the Cohoes Falls becomes what it looks like now, which is a fairly dry feature. Lake Fort Anne, the successor to Lake Colville, didn't make it into the Hudson Valley. At Fort Anne, New York, was the bedrock threshold where that lake flowed outward and then sent a high discharge flow down the Hudson Valley, similar to the size of the flow that came down the Mohawk Valley. So we have an interesting glacial history in the Hudson Champlain Valley with a lot of catastrophic high discharge events. And finally, the last lake left in the Champlain Sea is here. My daughter is happy and is singing, and there she is as we conclude. What's to do? Field work. Are those ice margins atop the Rensselaer Plateau really there? And if they are, or which ones of them are, or how do they eventually get redrawn? We have to connect them to the ice margins in the rest of Rensselaer County and over in Berkshire County, which ties in with work that I've done throughout much of my career and ties in with much older work, Bob LaFleur mapping the Troy 15-minute quadrangle for his PhD in 1961. A beautiful piece of work. Bob is my mentor at RPI. I was his last PhD glacial geology student. back in '85. And his last PhD student of all was in 1996 when he retired. 1994, Gary Wall at the USGS in North Greenbush did a hydrogeology dissertation with Bob. So that's how we tell the story. My daughter on her first snowshoes with her first hiking sticks last winter at Grafton Lake State Park. Thank you. That's it. Let me see if I can stop sharing here.
Do we have any questions? It was so thoroughly described that no one has questions, I guess.
Or I talk too fast.
That was very cool. Thank you very, very much.
So you're unmuted.
Well, I actually have some things if you guys want to see it relating to glacial geology in this area as well, with what I do for my job. And I've talked with Dave many times before about this stuff.
Hi, Carl.
Hi there. So actually the LiDAR imagery on RPA's website is something I built for part of the Postco Bends project. And that was something to highlight all the preserves in the plateau to see the true relief of the surface, because LiDAR is an amazing technology.
Mute us.
Like, actually, I can. I can have something for you guys here. I have a few things, LiDAR map of the whole Kappa region. So one thing that's especially true with these, as Dave highlighted here with the ice margins and meltwater channels, is actually understanding, okay, these meltwater transported sediments, where those sediments go. So Bob LaFleur, as Dave mentioned, was the first person really to touch this in the Kappa region, especially the 50-minute quad, which to this day is still an amazing map, and hoping to get it. Eventually it'll be back on the State Museum website where anyone can download it. It's a beautiful map, and his research has led into future projects in this area. The main thing now is understanding the age of these deposits and when this happened, as Dave also mentioned here, field work, how to correlate these ice margins, not just in the plateau across to Albany County into Massachusetts, Vermont, and understand the actual retreat of these sequences, because as the plateau is a high point, it's going to be a cold-based glacier, which means it's going to recede slower than in the lowlands where it's warmer and glacier like Albany times. So also understanding what's the timing of the deglaciation of the plateau versus the lowlands in eastern, actually western Rensselaer County. And that's where I hope to eventually do that. And one of the places actually the bends to see is a perfect example. It's the Postco Gorge, Barberville Falls. These are ancient meltwater channels, and likely the last ones that were used the most. And you had this eventually erosion back of these waterfalls, which is why Barberville Falls to this day isn't a canyon. It's just wearing back over time. And based on its elevation, it's a likely key to why the Postco Gorge and the Barberville Falls probably formed around the same time. These depths, and understanding that, we don't really truly know that. So yeah, like Dave here, you show these different meltwater, all these different moraines here, and all these little wetlands in front of them. And these little wetlands may have barbs at the bottom of them. We don't know. It's what they didn't know in the future. So at the museum, that's what we've been doing with the geological surveys, doing coring these wetlands in the winter to actually get to the ice and actually pull out radiocarbon materials in these wetlands, and that use that as a minimum date for the formation of this moraines to actually start this chronology receding of the glacier in the Finger Lakes region mainly at this point.
Carl, can you see the screen?
Yes,
Is that your screen or is that Dave's?
that is Dave's.
I was wondering if we could move over to the western side.
I have it on mine. If I could share my screen, I can show you guys. I have the whole Kappa region.
Okay. Dan, is that possible?
Carl, I just made you a co-host, so you should be able to share your screen now.
Yeah, Dave, feel free to chime in with it if you see anything too, as well. So you guys can see this?
Yes.
Yeah. So as you can see, the Rensselaer Plateau is here. I don't know if you can see my cursor at all. I'm highlighting the plateau on the right side.
We see that.
So you're actually seeing the whole Kappa region here across. So you can see there's really distinct change in geology from Rensselaer County side to the Catskills and Schoharie Valley on the left. This is basically east-west directly using geographic north-south, not magnetic. So it's on the over in the bottom left here is the Schoharie Valley. You can see the Gilboa reservoirs. So one thing we don't really know is what's the chronology. This low blue section in the middle is actually Glacial Lake Albany that Dave highlighted, with the Cohoes Falls up here. I wish I had a better marker. Yeah, I have a hand. Let's see. You see the hand?
Yep.
Right. So that's actually Cohoes Falls there, and the Half Moon Moraine is up here, just above it. So one thing we want to know is understand when was the timing of this of Lake Albany, and when was the retreat? Let me zoom in here. Oh boy, this is a big file. I'm actually going to. It's going to freeze on me, of course. But any which way, yeah, there's all these different things. So like this is an example of meltwater channels in Albany County. Like what do you find in these meltwater? This is actually stacked sands from meltwater pushing off to the south. When you can see there's a person for scale the size of this thing. This is a 150-foot exposure of sand, of almost pure sand. There's no gravels, no fines, no silts, no gravels, no clays, and it was an amazing find. And we find things like this is up close. You can really see the different cross bedding in it. There's aeolian, which is windblown sand, and then there's fluvial sands where you get cross bedding. So a lot of this is fluvial. There's some ripple marks up here on top, and the fine sands that are actually, it's almost like a cement.
We're still seeing a shaded relief.
Oh, sorry. Let me switch screens here. Stop share, share again. Now you can see it.
Yep.
Yeah, this is an example of these different sands, these rippled sands and these cemented sands showing this directional flow of the sediments. There's another showing you can actually see this U shape to it, this channel. And these are erratics that Dave highlighted, the one in Grafton. And just to give you scale, there's myself holding the rock up with a glacial till below it. So this is actually entrained in the moraine. This is a monster. This thing's about the size of a caravan. And there's more varves in outcrop. And this is a technique you can use now to actually date the sands in these meltwater channels. This is actually OSL sampling, which uses stimulated sands that starts basically what's the word I'm looking for? Exponential decay of a radioactive cracking of essentially the quartz crystal. It creates a clock. And this is another way of getting core samples in lakes. And this is an example of like folded, when the glacier is advancing over the stuff, it actually will fold this. This is a vertically bedded fractured clay. So it's just interesting to see all these things. This is like the fun side of glacial geology. Essentially, it's field work and then understanding what's going on and correlating this across these vast areas. So it's field work is a must. We've got a bunch of questions here.
We do. Where is that ice margin in relation to Babcock Lake? This would be the one Dave had in blue.
It wraps around from Lake Road, where the Cane Terrace, like you can pick up just off the eastern end of Lake Road, and taking it around Babcock Lake Road, where you then lose it as you're going up the hill, just a bit south of the junction of Lake Road and Babcock Lake Road. The address here is 957 Babcock Lake Road, so you'll all be showing up at my doorstep at some point. Bring food, but the Cane Terrace is partially removed from old gravel mining back in the 50s and 60s, either for road improvements on Babcock Lake Road or for the extensive road improvements that Route 7 went through, kind of through Pittstown and up the hill to Potter Hill. There was a lot of effort to redo dips and turns in Route 7 back then. So the Cane Terrace is traceable as a landform you can stand on, and if you were to dig in it, you'd find sand and gravel. And I think it's the real deal because there's a large number of boulders were deposited right where the edge of the ice stood. The part of the ice margin that wraps around Babcock Lake itself is a bit harder to distinguish because I don't have sand and gravel deposits that I've seen in my walks around the lake. Doesn't mean they're not there.
This is Ivan Vamos. I have lived at Babcock Lake in the summers for about 50 years. I think that by and large, it has been heavily eroded, steep sides. And in places, it looks like there was some rock failure actually. And then shattered rock at the lake bottom if you're diving down there. Fairly deep lake for the area. So it may be a graben as well.
Emily has a question for you. How many ice sheets covered this area during the entire period of the ice ages? And does each ice sheet obliterate the traces of the former? In which case, how are the earlier ice flows dated?
Good question about successive continental glaciations. They do tend to largely remove the deposits from the previous one, although not everywhere. And they didn't always follow exactly the same margins, if you will, that may have gone a little farther on one lowland and not as far in the other, which meant it left behind deposits from the older one that weren't subsequently overridden. But in places where the ice does override, especially in lowlands, especially if the ice is flowing across wet terrain, like flowing across a water body, it may deposit sediment on top. So there are places where multiple glaciation deposits are preserved. And that's where we get our handle on where the ice was in older glaciations. Some places where there is preservation.
Dave.
Yeah, Valerie has a question here. Can a line be drawn from the ice that covered the plateau to the Barnes ice sheet? I'm not sure what they are. The Barnes ice cap. Is that? I'm not sure what
That's
that.
a long way off. If I'm thinking of the Barnes in the Barnes ice cap in Upper Canada, that would be quite a chore to try and trace an ice margin that far. I think it might take me longer than I have left in years.
What techniques
Bob,
do you,
good to see you. I didn't know you were here, Bob.
Yeah, I wanted to let you know that Cadwell mentioned several times that he and Canale had found some multiple till and outwash exposures along the flanks of the plateau. I have
The
no idea
western
where they.
flanks?
Mhm.
The western flanks?
I don't know. I mean, you never took me to see them.
Yeah.
Probably took
yeah.
Kelly out there though.
I know there are gravel pits there off 351 when you're heading between Tamarack and Postingkill.
Oh, okay, yeah.
Kind of expect that there would be at the foot of the plateau on that side.
Yeah, I think they're on the western flank. If I remember right.
Yeah.
I think I've seen them before.
Yeah, there's
But-
a lot of old access roads into gravel pits there off 351.
Yes, it's good to see you, Bob, too. It's official geologist at the State Museum. He did many areas of mapping pre-LIDAR in the capital region.
Anyone can do geology. now,
Pre-aircraft.
but,
If it's Deneen, it's pre-aircraft.
Yes.
Happy
right,
belated
smartass.
80th, Bob.
You're not that much younger than me.
Naomi has a question here. What techniques do you use to correlate the fragments of glacial ice margin?
Well, it's nice to get a real age on something, and that tends to require you now with, as Karl mentioned, OSL dates. If we have other means of dating rather than just lucking out to find something you can carbon-14 date in a VAR, for example, that map of Jack Ridges that shows ice margins across the Hudson Champlain lowland with little dates on them. I know you probably couldn't read it during the presentation, but maybe you can zoom in on it later on your own. There are places where there's something datable in the VARV record, or there was something off to one side or another side that might have been a date from the bottom of a bog that was along an ice marginal deposit. And someone gets a carbon-14 date and says, okay, I'm matching up the ice margin. There is a bit of personality involved in actually extending ice margins where there's no physical evidence that you can see them on the landscape. You get into games, and I'd call them games, where you're projecting the change in the thickness of the ice up the valley side and across the interfluve between that valley and the next valley, and you project it downward and you see how far the ice might have went. And then if you go there and you find a deposit, well, then you'll probably go ahead and draw the line. But oftentimes you really can't do that, and it's something that old timers like Bob Deneen and myself sometimes say, well, I don't have it ice margin matching there, I have it matching here. And we're probably both correct, or we're both incorrect.
Well, another question here. Mike asks, where in time is the formation of Thatcher Park, the Silurian roundout, in relation to the Rensselaer Plateau? Seems to be later, he says. Plant and seashell fossils found there. Of course, you wouldn't get those in Graywacke.
Yeah. Different geology, Thatcher Park, Helderberg group of Silurian, Devonian, predominantly limestones. There's some good reefs preserved up in the vicinity of Thatcher Park. I remember doing one in a paleoecology class at RPI where we studied a little reef mound that's preserved up there, not too far from the entrance to the park.
So how do they compare in time? Which one?
Oh, this is the Thatcher Park rock is a lot younger than the Rensselaer Graywacke. The Rensselaer Graywacke is Cambrian Ordovician in age, say 150, 200 million years difference in age between that and Thatcher Park, Helderberg rocks. They were in shallow water, marine environment, tropical location.
Stable landscape.
During the Devonian. Yeah,
Okay,
Bob.
looks like we got a bunch of geologists on the line here. That's been great. Are there any more questions? If not, I think I'm gonna thank Dave and also Karl, who has given us a little insight also. And turn it back over to Dan Morse.
Well, that's it for tonight, everyone. Thank you very much to all of our speakers, everyone who chimed in, everyone who contributed questions. Thanks to Jeff Briggs for hosting, and we'll hope to see you next time. Have a great night.
Hey, thank you.
Good night.
Night, everybody.
Good night, thank you.
Thanks.